the universe is quite a dark place, is maybe one of the best explanations of what we are facing right now in modern cosmology. Our current best fitting model, the lambda CDM model, is a parametric description of the universe of which 95% of the energy density is made up of dark sector. We have 25% of dark matter right now, and dark energy or lambda cosmological constant of 70% of the universe. While the 5% of the universe that we do know is mainly composed of baryons, some neutrinos, and photons. This lambda CDM model only needs general relativity and 7 parameters to describe the universe to quite a nice extent. We can describe the fluctuations of the cosmic microwave background of the universe just using general relativity and adding the cosmological constant. The position and correlation of galaxies can be mainly explained just by general relativity, and even motions of the planets around the solar in the solar system is explained by general relativity. This is also the place where general relativity was found to be an accurate description of the theory of gravity that is behind that. But this lambda CDM model faces some difficulties in recent times. Measurements of the local level expansion speed of the universe, often parameterized with h0, which has some funny units, kilometers per second per megaparsec, give us a measurement around 67, with a value around 67, while local measurements of the local expansion speed gives us measurements around 74, which is not within the errors of those two measurements. So we have to come up with new methods of dealing with this problem, dealing A with these tangents and B with the fact that we know nothing about 95% of the energy density. We go to modified gravity theories. The theories that I talk about in this little talk will be those that add new forces. There are different modifications to gravity that can be done. For example, you can add new dimensions or new deviations from Lorentz invariance to change your theory of gravity, but adding new forces might be like the most simple way to think about it. A new force can be then absorbed in a change of the couplings, so in a sense the constant, universal gravitational constant of Newton goes over to different constants, we can call them, that can be different between matter and photons. So light and matter react differently to gravity while they act the same in general relativity. And adding a new force, of course, comes with a new messenger particle. I've denoted it phi. And these modified gravity theories have then the effect that on the scale of the universe, these new messenger particles that come with a new field act like a lambda, like a cosmological constant on late times, while on early times they actually act like cold dark matter, which is a nice way of handling both problems of these of the lambda CDM model. We only now need the modifications to gravity, and we can explain the parametric description of the universe today. They also come with a change in clustering and a modification of lensing. This is an effect of changing the gravitational constant, of course. While on the level of the solar system, we don't want there to be much change. I mean, like we said, the main reason why we believe in general relativity is from observations in the solar system, like the precession of the orbits of the planets and the lensing of light. And this poses a huge constraint on the models that we look at. the modifications of gravity need to, in some sense, be screened on scales that are on the solar system, or on scales where matter is very packed, which are then called these chameleon mechanisms of screening. But the second part is the effect of on galaxies, on the scale of galaxies, is the one that I wanted to talk about. Because the new ESA mission Euclid is going to be a nice way to also further constrain these modifications of gravity. The ESA Euclid mission is planned to measure 1 billion galaxies across 1/3 of the sky, and we will look back at galaxies up to 10 million years back in the past. And with all these new data and the precision of the data, we are going to be able to measure the correlation between galaxy positions and shapes up to 1% precision. This is going to help us understand and the modifications of gravity that might be or might not be present in the current universe.